Hello students, welcome to your favorite YouTube channel, Tomachang Tutorial, myself Kishan Kulung, and today we are going to discuss about graphical representation of Boyle's law. First of all, what you need to keep in mind is Boyle's law graphs are called isotherm or isothermal curve because the temperature is kept constant in Boyle's law. Boyle's law graphs are called isotherm or isothermal curve. Boyle's law graphs are called isotherms or isothermal curves because the temperature is kept constant in Boyle's law. As we know that in Boyle's law, mass and temperature are kept constant. So when temperature is kept constant in Boyle's law, we call the graphs of Boyle's law as isotherm or isothermal curve. Now let us quickly begin with the graphs of the Boyle's law. Number one, P versus V. P versus V means pressure versus volume. Now, I have already drawn the graph to save time. This is x-axis and this is y-axis. This x-axis and y-axis meets at this point. This is called point of intersection, and here the value of x and the value of y both becomes 0. If I plot volume in x-axis, which means if you go from 0 to right hand side, volume of the gas increases. Similarly, if I plot pressure in y-axis, this means if you go from 0 to upward, the pressure of the gas increases. So, when we draw pressure volume versus volume graph, the curve look like this, okay? But make sure that this curve does not touch y-axis or x-axis. If this graph touch y-axis, then what does that mean? This means that the volume of the gas can be 0. And if this curve touches x-axis, what does that mean? This means that the pressure of the gas can be 0. Since pressure and volume of gas can never be 0. Since pressure and volume of gas can never be 0, so this curve should neither touch y-axis or x-axis. Do you get my point? I'm repeating it again. If this curve touches y-axis, means volume of the gas can be 0. But I wrote here volume of the gas can never be 0. If this curve touches x-axis, then the pressure of the gas becomes 0. And I have already written here the pressure of the gas can never be 0. So pressure and volume of the gas can never be 0. So this curve should neither touch y-axis nor x-axis. This curve would somewhat look like this. Okay. Now let us see the values of P versus V, how it changes. When pressure was 1, 2, 3, 4. When the pressure of the gas was 4, see here, volume, if you draw a straight line down, you get 1. Okay. When pressure was 4, volume was 1. Now when you reduce pressure to 2, the volume is increased to 2. 1, 2. When you reduce the pressure, volume increases. When you further reduce the pressure to 1, the volume is further increased to 4. 1, 2, 3, 4. If you draw this straight line, you will get this. Means when you increase the pressure, when the pressure was 1, volume was 4. When the pressure became 2, volume became 2. Means when you increase the pressure, volume reduces. When the pressure became 4, volume reduced to 1. This means when you increase the pressure, volume reduces. When you decrease the pressure, volume increases. Okay? Pressure is inversely proportional to volume, or you can also say volume is inversely proportional to pressure. If pressure increases, volume decreases. If pressure decreases, volume increases. Okay? This curve proves that pressure is inversely related to volume. What does it prove? This graph proves that pressure and volume of gas is inversely related. Inversely related. If you increase the pressure, volume decreases. If you decrease the pressure, volume increases. Okay. One more thing I would like to let you know. When pressure was 4, volume was 1. Volume was 1. When pressure was 4, volume was 1. And product of PV, pressure into volume, PV equal to 4 into 1. 4 into 1, 4. When pressure was 2, volume was how much? Volume was also 2. 1, 2, 3, 4, 5. Volume was also 2. So product of pressure and volume, how much did you get? 4. When pressure was 1, volume was 1, 2, 3, 4. Volume was 4. So product of pressure and volume, you got 4 into 1, 4. When you change the pressure, volume also changes, but the product of pressure and volume remains fixed. That is same. Okay. This is just an example I'm showing, but it is very, very true. When you change the pressure, volume also changes in such a way that the product of pressure and volume will always remain constant. You must keep this in mind. Okay, the second graph. Let me start with the second graph. Number 2. We have two parts, PV versus P, and number B, PV versus V. Okay. Let me draw number A. This is y-axis, this is x-axis. Y-axis, x-axis, this is the point of intersection. Okay. If I plot pressure in x-axis and product of pressure and volume in y-axis, how would the curve look like? The curve would look like this straight line. But make sure the straight line does not touch y-axis. Why? If this straight line touches y-axis, means pressure of the gas can become 0. Pressure becomes 0. And you know that pressure of gas can never be 0. So this straight line should not touch y-axis. Okay. Now let us see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. When you say the pressure was 1, the product of pressure and volume was how much? 3. 1, 2, and 3. When the pressure, you increase the pressure to 2. When the pressure became 2, the product of pressure and volume became 3. When you increase the pressure to 3, product of pressure and volume 3. When you increase the pressure to 5, 1, 2, 3, 4, 5, the product of pressure and volume 3. No matter how much you change the pressure, but the product of pressure and volume does not change. It will remain same. That is 3, 3, 3, 3, 3. This is just an example, but it is very, very true that when for whatever be the value of pressure, for fixed mass of gas and constant temperature, that should be kept. That should be understood. Mass of gas should be kept constant and temperature of the gas should be kept constant. Then for whatever be the value of pressure, the product of pressure and volume will remain same forever. This graph proves that for changing pressure, the product of pressure and volume does not change, which means the product of pressure and volume remains constant. Okay, I hope you got this. Now let us do question graph number B. PV versus B. This is y-axis and this is x-axis. This is the point 0. I plot volume in x-axis and PV in x-axis, y-axis. Okay, if you go from 0 to right hand side, volume increases, and if you go upward, PV increases. So if I draw PV versus B, how would the curve look like? The curve would look like this straight line, similar to the previous one. Why? First of all, let me explain. This line should not touch y-axis either, as before, because if this line touches y-axis, this means volume of gas becomes 0. And you know that volume of gas can never be 0, so this line should not touch y-axis. This should start somewhere from here. Okay. Now, when you increase the volume, suppose the volume was 1 here. If you draw the straight line, the product of pressure and volume was 1, 2, and 3. When you increase the volume 2, product of pressure and volume was 3. When you increase the volume to 3, product of pressure and volume 3. When you increase, no matter for whatever be the volume, the product of pressure and volume always remains constant. With changing volume, the product of pressure and volume will not change. Okay, this graph proves that for changing volume, the product of pressure and volume of gas remains constant. Okay, with changing volume, the product of pressure and volume of gas remains constant. Whatever be the volume, how many times you change the volume, you keep the volume 1 or you keep the volume 100, whatever be the volume, the product of PV will be a straight line, will always be the same. Do you get this? But keep that in mind, temperature and mass of the gas should remain constant. Okay, now the third graph, P versus 1 upon V. Okay, this is y-axis and this is x-axis. First of all, let me tell you, if I write a fractional number 2 upon 5, here 2 upon 7, here 2 upon 9, which one of this is the greatest and which one is the smallest? The greatest is 2 upon 5, and then 2 upon 7, and the smallest is 2 upon 9. As you increase the value of the denominator, the value of the fraction decreases. As you increase the value of the denominator, the value of the fraction decreases. Okay, 2 upon 5 is greater than 2 upon 7. 2 upon 7 is greater than 2 upon 9. I hope you got this. Now, if I plot 1 upon V in x-axis and P in y-axis, how would the curve look like? The curve would look like this. Make sure this line also shouldn't touch this, because if it touches, it becomes pressure and volume 0, and pressure and volume of gas can never be 0, so the graph will start somewhere from here. Now, if we increase the pressure, 1 upon V also increases. See, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. For this value, for this value, for this value, for this. Okay, here 1, 2, 3, 4. When 1 upon V was 4, P was 1, 2, 3, 4, 5. Okay, now this. When you increase 1 upon V, P also increases. When you increase P, 1 upon V also increases at the same time. 1 upon V increases means what? What does it mean? If 1 upon V increases means V decreases. 1 upon V increases means volume decreases, because volume denominator, the number in the denominator should decrease so that the value of the fraction will increase. If you go from left to right hand, from right hand side to the left hand side, if you go from right hand side to the left hand side, the value of the denominator is decreasing. The value of the denominator is decreasing, but the value of the fraction is increasing. So 1 upon V is increasing when you go from 0 to right hand side. From 0 to right hand side, when you are going from 0 to right hand side, 1 upon V is increasing means V is decreasing, okay? Denominator is decreasing. So when you plot pressure versus 1 upon V, the graph would look like this. When pressure is 1, volume is 1 upon V is 1. When pressure is 2, 1 upon V is 2. Okay, suppose. When pressure is 3, 1 upon V is somewhere like this. Means when pressure increases, 1 upon V also increases. When pressure increases, 1 upon V also increases. 1 upon V increases means volume decreases. V decreases because denominator has to decrease in order to increase the fractional value. I hope you got this. Now let us move on to the next one. V versus 1 upon P. The same thing here. This one is the last graph. This is 1 upon P and this is V. The same thing, the graph would look like this. If you increase V, 1 upon P also increases. If you increase P, V, if you increase the volume, if you move upward, the volume will increase. See, here it was 1, here it became 2, here it became 3, here it became 4, here it became 5. Similarly, 1 upon P also 1, 2, 3, 4, 5. When you increase volume, value of 1 upon P also increases, which means pressure decreases, because to increase the fractional value 1 upon P, denominator has to decrease. So when you increase V, 1 upon P increases. That means pressure decreases. Okay. This graph proves nothing but when you increase volume, pressure decreases, and when you decrease volume, pressure increases. The same thing. The reciprocal of pressure increases. What does it prove? With increasing volume, the reciprocal of pressure also increases. Reciprocal of pressure increases means pressure decreases. Okay. The graphical representation of Boyle's law is this much. Now, before closing this session, I would like to ask a very simple question. So you people, I hope that you people will comment the answer and let me know how much you understood the way I taught you. Okay. The question is, while inflating a balloon, the volume and pressure of the gas both increases at the same time, isn't it? While inflating a balloon, the volume and the pressure of the gas both increases at the same time. At the same time. How would you justify your answer? Okay, this is the question, and please, I request you, please do comment below your answer and let me know how much you understood from the session, from the topic which I taught you. Thank you so much. Stay blessed, stay safe, and stay happy. And hey, don't forget to subscribe and click the bell icon so that you can get more videos like this. Thank you.